Greetings, greetings, greetings. Did anybody have any questions about anything before we get started with the material from today? Today's material is from Lecture 10, which was a couple of topics relating to bending stress that come after the primary learning associated with bending stress, so off-axis moments and composite beams. And once you know how to calculate bending stress, both of those are easy things to tack on to it. So because they're minor topics related to bending stress, today's tutorial is actually going to be pretty short. I've only got two problems to do with you today. So we've certainly got time for questions. Well, we always have time for questions if anybody has them. So go ahead and shout them out if you've got them, or type them in. Whatever you want. Your preference. I'll start doing some writing of the first problem on the board here while you're asking any questions that you have to ask. No. I think I kind of get you. So we're looking for what the length position of that point is, right? Because we know that there's going to be a local maximum here in the moment diagram that we want to find. So the question relates to finding that length there. Yeah. So the way to find this length, and it varies a little bit depending on whether this is a curved line as part of a quadratic that you're dealing with, or whether it's a linear line that you're dealing with. It's a curved line? Yeah, okay. So if we've got a curved line like that in the shear diagram, I should have given myself a bit of space above this. But we'll jam the free body diagram of the beam in here. So what you've got here is you've got an increasing negative slope. So you must have increasing negative loads here. So this is going to be coming from a load distribution that looks something like this in this particular case. So the best way to find the equation of this line is to write the equation that describes the distributed load and then integrate that equation to get your equation for shear. Okay. So if let's say our beam did look like this, and this is I don't know, this is 500, and this is, well, let's give it some newtons, 500 kilonewtons per meter, and this is a length of 3 meters there. Then when you write your equation for what the distributed load is, I always recommend doing a separate little plot of how W varies with length, because here W starts off to be 0, and you can easily see that there. But at this point here, 3 meters, the value of W, because it's a downward load, it's minus 500 here. So your line that you want to create the equation for W for is this line here. And now when you draw it like this, you can really clearly see that that line should have a negative slope, or the equation should have a negative slope, where if you try and directly write your equation from the picture of the distributed load, you might get the slope backwards. So here we just have W is the slope, so change in y over change in x. So we have minus 500 over 3L plus the y-intercept, which in this case is 0, so we have nothing there. So the equation for V then is just the integral of the equation for a distributed load. So we have V is minus 500 over 6L squared plus C, where C is our constant of integration here, which is this value. This is value C. And that value is going to be equal to whatever the support reaction here is. So C is going to be equal to AY there. So then once you get that, then it's just a case of setting that equal to 0 and solving for your value of L. So I think I answered your question about that part, but then you mentioned, or can you do it another way? Okay. No, there's no other way to do that. Like I think you were talking about doing like a section cut to figure it out. So that doesn't actually apply here, because the only time when you can really do a section cut to figure out something on your shear and moment diagram is when you know exactly where you want to take the section cut. So if you're trying to figure out some distance L here, taking a section cut doesn't work, because you don't know exactly what the length is here. That's what you want to find. If you knew, for example, that let me do some erasing here. Let's say you had a moment diagram, and we might actually even see this here. If you had a moment diagram that, let's say, looked something like this, right? And you knew exactly where you wanted to look for your maximum moment, let's say it corresponded to L equals 3 meters, then in order to figure out the maximum moment, rather than going through the process of figuring out the equation for your shear curve and integrating that, you could just do a section cut straight at L equals 3 meters and analyze the free body diagram to figure out what your maximum moment is. Does that make sense? Yeah, okay, great. Okay, seeing a question here relating to the project, and it asks, for the first submission of the project, do you want any pictures of our connectors by themselves, or only the picture of the assemblies? Just the pictures of the assemblies would be great. And depending on what your connector looks like, it might be helpful to do an exploded view of the assembly too. For instance, if you have some pins going through, depending on how much, whether you're setting materials for the different elements to define, like sort of to visually separate them by color. Sometimes in assembly drawings, components can kind of get hidden if they're all the same color and you've got a pin that fits perfectly into a hole. Then the outline of it maybe is not so apparent. So doing an exploded view would help in that case. But really what you want to be thinking about for those drawings is, what do I need to show Sam to clearly, so he clearly understands what it is, how our coupling works, or how this one of the couplings works, right? You want to clearly communicate the concept that you're trying to show, okay? Yeah, no problem. These are great questions. Anybody have other questions that they'd like to ask related to project, labs, problem sets, quizzes, life? Okay, let's keep drawing. All right, so that's 200. This is 200 too, actually, along the top here. Okay, and what have we got? We've got a centroid there, horizontal centroidal axis, vertical centroidal axis, and we've got an off-axis moment where the moment is going around in this direction. So this is moment M, and the angle in here is going to be 60 degrees like that. And then let's say that this beam is going back into the plane of the glass like that. There we go. Okay, so problem statement for this one here. The beam is made of Douglas fir. Douglas fir. The grain direction in the wood is parallel to the length of the beam. Okay. Douglas fir, the type of wood that BC is famous for growing in vast quantities and prized because of its very straight growth habit with very much a lack of branches sticking out along its trunk flank, which gives you what is called clear wood, so wood without knots in it. Okay, so the grain is parallel to the length. Determine the maximum moment M that can be applied to the beam if the required safety factor is 1.8. Okay. So there's our question. Okay, so simple little problem. T-shaped beam made out of Douglas fir wood, off-axis moment that's going to be at 60 degrees to the horizontal. What is the maximum value that moment can be if the safety factor requirement is 1.8? First thing we do is go over and look at the SI side of our material property table to figure out what the strengths for Douglas fir are. And being wood, we know that we're going to be looking for the ultimate strength value, not a yield strength value. And also being wood, we know that we're going to have differing ultimate strength values depending on whether we're looking at tension or compression. So let's just put them both up here. All right, for Douglas fir in SI, we've got what, tensile strength of 85 megapascals. 85 megapascals, right? As you'll note, compared to the other grades of wood there, or the other types of wood, that's fairly high. So another reason that Douglas fir is quite a prized wood. And compressive strength 49.9 megapascals. Okay, great. So now I can put this down and we can talk about the problem. There we go. Okay, so like I explained in the lecture, problems with off-axis moments are really easy. The way to handle these is just resolve the off-axis moment into two components, one that acts around the horizontal centroidal axis, one that acts around the vertical centroidal axis, and start by considering the contributions from those two components of the moment separately in terms of how they apply bending stress to the object. So we're going to put the horizontal component down here. And again, you can use your right-hand rule to get the directionality of these correct. So we've got M subscript X for the moment about what I'm going to call the XX axis, and this would be the YY axis, and then the component along the Y axis here. Again, right-hand rule, thumb in the direction of the vector, fingers curl in the direction of the moment here. So M subscript Y. Okay. Now I'm just going to grab this and redraw it just so that there's not something that's all cluttered by these dimensions, so I can do a bit of annotation for you, labeling where, or showing where compressive and tensile stresses are going to be maximum. So I've got mx this way, like this, M subscript X. Okay, I'm gonna think about mx first. Right, whole beam is going into the plane of the glass here. Okay, so if I take this cross section and I twist it in the direction of mx, then I am taking the top half, everything above the xx axis, and I'm pushing it into the rest of the beam here. So this whole top portion of the beam, well, this portion and up here, right, that portion of the T, that's all going to be under compressive stress. And the level of compressive stress is going to increase as we move away from the axis of mx, right? Sigma equals my over I. So as we go away from the axis of bending, that's increasing distance y here. So the maximum compressive stress from mx will be at the top of the beam here. Okay. So this is the max compression from M subscript X, right? And then conversely, as we move downwards, we're going to have increasing tensile stress moving away from the neutral axis of bending. So if I show tensile stress, or the location of maximum tensile stress, just by sort of hatching along the line like that, maximum tensile stress is going to occur along the bottom of the cross section here. So this is the maximum tensile stress from M subscript X. Okay. So now what you want to do is you want to consider how bending stress is caused by My. Okay, so here is My there. All right, where is the maximum compressive? So we started with compressive stress for mx, so let's start with compressive stress for my. My is taking the whole cross section and twisting it in the direction of my hand. So it's taking the whole, what is for me the right hand side of the cross section, and pushing it back in on the beam. And so the level of compressive stress just from My is going to increase as we move away from the YY axis. So maximum compressive stress is going to be along this line from My. So this is max compressive stress from M subscript Y. Okay. And then conversely, the maximum tensile stress is going to be at the other extreme, right? So this is the max tensile stress from My. Okay. So look at this. We've got maximum compressive stress from mx at the top, maximum compressive stress from My on this edge. At this point here, the two maximum stresses for compressive stress will add up. So this is going to be the point where the largest compressive stress exists in the beam. Okay, this is point of sigma, the maximum compressive stress. That's sigma comp comma max. Okay, maximum compressive stress right there. Once you've figured out where one of the maximum tensile or compressive stresses are, the other maximums in the opposite diagonal corner of the cross section. Right, so the maximum tensile stress is going to be down here. Actually, let's write that in a similar way. Sigma tension max, right? So at this location, we have maximum tensile stress from mx, and we do have tensile stress from my too, but it's not as high as the tensile stress over here. But still, we've got tensile stress being added to tensile stress in this corner. Whereas in this corner, for example, we've got maximum tensile stress from my, but we've also got maximum compressive stress from mx. So the two are sort of opposing each other, and they're going to cancel one another off to some extent. Okay? We could do a calculation to figure out if the net effect at this point was a tensile or compressive stress. But the thing to realize is that if the point of maximum compressive stress is here, then diagonal that in the other corner over here is going to be your point of maximum tensile stress. All right. Now, being a cross section like a T, the value of compression here at this point of maximum compressive stress is not going to be equal to the value of the maximum tensile stress. So it's unclear whether or not the limiting factor here in terms of meeting the safety factor of 1.8 is going to be failure by compression or failure by tensile stress. So you need to check both locations in this case. So what we're going to do is we're going to find the maximum value of M for failure of the wood in compression and for failure of the wood in tension, and then the maximum value of M would be the smaller of those two M values. Okay. So in order to do all this, right, we need to figure out some properties of the cross section first. We need to figure out what the location of the centroid Y bar is, and then once we've got that, we know that we're going to need some properties of the cross section, both IXX in this case and IYY, so we can get those too. So let's start with finding the location of the centroid here. And I'm just going to check to see if anybody has asked a question related to anything that I've said so far. No. Okay, so we're using our second moment of area equation here. And breaking again the object up into two shapes, a top piece and a bottom piece, both that have known centroid locations, right? So this thing expands into A1y bar 1 plus A2y bar 2 all over the summation of A1 plus A2. So let's go ahead and do that. You know all this from last tutorial and lecture. So we've got A1 is, what did I call 1? I called 1 the top piece, 200 by 50. So 200 by 50, and then its centroid location relative to the datum that I'm taking to be the base is 225. So 225 there, plus the area of the bottom piece, also 200 by 50. Okay, and its centroid location from the base is 100 millimeters up. There we go. And then we're doing the combined areas. So we've got 2 times 200 by 50. Okay, so we've got 200, 200, 200 can all cancel, 50, 50, 50 can all cancel. And you see what happens is what we end up with is the centroid location of piece 1 plus the centroid location of piece 2 divided by 2. So we're just taking the average of the centroid locations for those two different pieces. Why? Because both pieces have the same cross-sectional area. So in cases where both pieces have the same cross-sectional area, the overall centroid location is just an average of the centroid locations for the individual pieces. So that gives us 162.5 millimeters. Okay, now we can do the parallel axis theorem to figure out what the moment of inertia is about the x-axis. So we've got sum of I plus AD squared. Okay, so let's do that together. I'll shift that over to the left a tiny bit. So for the top piece, I is 1/12 base height cubed, 1/12. Base, remember, base is always the dimension that is parallel to the axis that you're interested in. So the base dimension here is the 200. So we've got 0.2 if we're putting that in meters. And height cubed, 0.05, cube that. Then we add on the area, so that's 0.2 and 0.05. And our distance d squared. Again, if I draw the location of the whole centroid as just an open circle here, we're looking for the distance between the centroid of the whole cross section and the centroid of the component shape that we're doing. So for that, we need to go from the base all the way up to the centroid location from the top piece, which is our 225, and then subtract the value of y bar to get that difference. So we've got 0.225 subtract 0.1625, and don't forget to square it, and then add on the same thing for the second piece that we're considering. So here we've got 1/12 base dimension that's parallel to the axis, so we've got 50 millimeters now. Our height 200, cube that, add back on our area, 0.05, 0.2, and then distance d squared, that distance right there. So in this case, we're going up by y bar and coming back down to give us the distance between those. Okay, so we're going 0.225, and nope, sorry. We're going up the distance of y bar, which is 0.1625, and then we're subtracting off the centroid location for this upright piece, which is 100 millimeters. And square that. Okay, jolly good. What does that give us? IXX 1.1354. 1.1354 times 10 to the minus 4 meters to the 4th power. Great. All right, now let's do IYY. Okay, for I about the y-axis, let's look at this. There we go. Okay, the centroid of the top piece is there. The centroid of the bottom piece is there. The centroid for the overall cross section is there. Notice that all three of those centroids lie on the y-y axis, so they're all collinear about the same vertical centroidal axis. That means that we can just use simple superposition to calculate what IYY is. So we can say that IYY is simply equal to the I for shape number 1 plus I for shape number 2 about their vertical centroidal axes. Okay, so for piece number 1 here, we've got 1/12 the base. Remember, our base and height are flipped now. Our base is the dimension that is parallel to the axis that we're dealing with. So the base is 50 millimeters, 0.05, and the height cubed is 0.2 cubed. And then we just add the exact same thing on for shape number 2, or the upright piece. So we've got 1/12. Its base is the 200. Its height is the 50. Cube that. Okay. There we go. I see the question there. I'll write this number down and then answer it. 3.5 for 2 times 10 to the minus 5. 3.5 for 2 times 10 to the minus 5. And that is units of meters to the 4th power. Of course, I didn't need to look to figure that out. All right, so now we're set. So now I'll check out the question. Okay, why would you use a T-beam? Doesn't symmetry have more stability because of weight and stuff? Okay. So, for example, here we've got 2 boards that are equal dimensions, 250 for both of them, right? If we wanted to create, so if we wanted to strengthen just the vertical piece here, then we might be able to get away with having something that's as strong as we need just by taking one additional piece of wood and putting it on the top to create the top of the T without also adding one at the bottom. Maybe we could make an I-beam and make all of the wood smaller dimensions, right? So we'd have less wood overall and have that satisfy our need. But maybe the wood is commonly sold in sizes of 250, so it just makes sense to use this. So it can be, and of course wood isn't sold in 50 by 200 millimeters, but that's just an example. So it could be for reasons like economics or just availability of materials and not over engineering it. But you're right, this would get stronger if we added a bottom piece to make it an I-beam instead of a T-beam. Okay, let's continue on. So let's do our calculation for the maximum moment for our required safety factor at the point of maximum compression first. Okay. So maybe I'll do this one over here. Okay. So actually we've got pretty much everything we need over there. We know that these are 200 by 50s now. So let me clean a bit more space up, and then we can do compression and tension right on top of one another. And we won't have to do any more erasing for this problem. Okay, so for compressive failure, okay, what we want to do here is equate the compressive ultimate strength divided by our safety factor, right, to the maximum compressive stress that occurs in the beam, right? The maximum compressive stress that occurs in the beam, we know it has a contribution from mx and a contribution from my. So here we've got sigma from mx plus sigma from my. What are these going to be? Well, the contribution to the stress, compressive stress at this point from mx is going to be that moment m subscript x, right? This moment, this component of the moment right here, multiplied by the distance This point is away from the x-x axis, so we can call that our distance y here, mxy over ixx. We need to use ixx if we're using the component of m that's about the x-axis. And then for our component of the stress caused from my, we want to be considering the component of the moment that's about the y-axis, m subscript y, and then the distance that our point of interest is away from the y-axis. So here we go. Let's just call that distance a there. So we're multiplying by distance a and then divided by iyy. Okay. So let's put all of the numbers in and then solve that problem. So the ultimate compressive strength was 49.9 megapascals. Our safety factor was 1.8 equals mx, that's the component of the moment that was along the x-axis. This angle here was 60 degrees. So it is m multiplied by the cosine of 60, that would give us mx. So m cos 60. Our distance y would be equal to the total height of the cross section minus y bar. So that is 200 plus 50, 250, minus 162.5. Okay, divide that by ixx, down there, 1.1354 times 10 to the minus 4. And then we're adding on the second term here. So my is going to be m multiplied by the sine of 60, m sine 60. And then our distance a, the distance that our point of interest is away from the axis of bending for component my, is 100 millimeters, half of 200, 0.1, divided by iyy, 3.542 times 10 to the minus 5. Okay, 3.542, yep, got it, times 10 to the minus 5. So we only have one variable in this equation, m. So solve for m, and that would be the maximum moment that can be applied to the beam at an off-axis angle of 60 degrees to the horizontal before our safety factor of 1.8 is met. So that comes out to be, or when I did it, it came out to be 9.8 kilonewton meters. Okay, right. But we're not quite done, right? Because as I said, the tensile stress, the maximum tensile stress, is not necessarily, or it's not going to be equal to the magnitude of the maximum compressive stress, and the strengths are different. So it's not clear which one of these points are going to be the limiting points in terms of maximum moment. So we need to check what the moment for tensile failure will be as well. So let's go ahead and do that. And we'll just do it right up over on this corner of the board. So my prediction about having enough room for this was wrong. Okay. But we can sort of go back to this line here and just bring that over there and then save ourselves some space that way. So we want to do now the ultimate tensile stress divided by the safety factor is going to be m subscript x multiplied by, so now we're dealing with this point, multiplied by the distance that point is away from the axis of bending for mx. So that's equal to distance y bar in this case. So we put y bar in there, and then we've got ixx plus m subscript y multiplied by the distance that this point is away from the y axis. So we'll call that distance what, b here? B divided by I, y. Okay, let's put some numbers in here. So 85 times 10 to the 6 divided by 1.8. 85 megapascals being the ultimate tensile strength, which is what I remember to have said. And am I remembering correctly? I am. M sub x, we've already said that that's m cos 60. M cos 60 y bar, we know what that is, 0.1625 divided by ixx, 1.1354 times 10 to the minus 4 plus, now we add on the second term here, my, m sine 60 multiplied by distance b here, which is half the width of that piece, so 25 millimeters. Okay, all divided by Iyy. Oh, it's so close. Just shift it up there a bit. 3.542 times 10 to the minus 5. Okay. And then again, we can solve for m there. Okay. So let's check out what that gave me when I did the calculation. $35.6. Okay, so we can apply a moment of 35.6 before the allowable tensile stress is surpassed. We can only apply a moment of 9.8 before the allowable compressive stress is surpassed. So therefore, our maximum moment is the smaller of those two, 9.8 kilonewton meters. Okay. There we go. Okay, easy stuff. Easy stuff. The problems involving off-axis moments don't get more complicated than that. Questions about where things came from there? Anything that was thrown up on the board? Just wait a minute in case anybody's typing. Okay, let's go ahead and do the second problem. So the second problem is going to be a composite beam problem instead of an off-axis moment problem, and then you will have had one off-axis moment problem, one composite beam problem. You'll be well set up to do the problem set. Radio. So what we have, and I haven't really drawn this as it is, but this is actually a ski. Okay, there we go. It's a pretty aggressive tip there. But I'm just drawing it with the tip is sort of just a straight beam there, but we've got a ski. This force here, that's the weight of a person standing on one foot on their one ski. And we're going to say that they're a 180 pounder. And of course, supporting the load here underneath the ski is a reaction from the snow acting upward. And we're going to say that this has a profile that looks like this, where the majority of the load is carried by the central portion of the ski, and then you've got a decreasing upward load at both the front and the back. Okay, so this load right here is W. Okay, and let's see some distances. So we've got let's make this 1.5 feet there, and then here's another 1.5 feet, and here's another 1.5 feet, and here is another 1.5 feet. Okay, 6 foot long skis. Okay, it's pretty long for skis these days. Wasn't so long when I was growing up. The cross section of the skis, or the cross section of the ski, looks like this. It's a composite that has a foam core. Okay. Here's the foam. And fiberglass on the top and bottom. Fiberglass. Okay, there we go. And this is a width of 4 inches there. Okay, I'm going to read the problem statement. A 180-pound man stands on a single ski. The ski has a foam core with a modulus of 300 KSI. So I'm going to write this E foam equals 300 KSI. There we go. The ski has a foam core with a modulus of 300 KSI sandwiched between 2 1/4-inch thick fiberglass sheets. So each one of these is a 1/4 inch in thickness. 1/4 inch thick there. Sandwiched between 2 1/4-inch thick fiberglass sheets of modulus 16 times 10 to the 3 KSI and ultimate strength 20 KSI. Okay, so I'll just say glass equals 16 times 10 to the 3 KSI, and the ultimate strength, sigma U, of the fiberglass, we're told is 20 KSI, excuse me. If the maximum bending stress for the given loading situation, this one here, should be 10% of the fracture stress of the fiberglass, determine the required thickness of the foam to the nearest 1/16 of an inch. Okay. All right. If the maximum bending stress for the loading situation shown should be 10% of the fracture stress, so for loading situation, the maximum stress due to bending should be 10%, 0.1, multiplied by the fracture stress of the fiberglass. So 0.1, we'll say sigma u glass. Okay. Then we want to determine the required thickness of the foam. Okay, and the required thickness is the distance here. We'll call h for height. And required value of h is our question mark. Okay. All right, everybody clear on what the question's asking there? Okay, so this being a composite beam, whenever you're dealing with composite beams, what you want to do is transform the cross-section of the beam into a single material that would undergo the same deformation profile relative to the original composite beam. So what we do is we take our composite beam like this. Okay, here it is. Now, all of the bending moments here are going to be happening about this horizontal centroidal axis, right? So we're going to do a material transformation, and we're going to transform the foam into fiberglass, and do that in a way so that the whole fiberglass ski, in this case, would deform the same way as this fiberglass foam composite. So we're not going to do anything to the fiberglass on the top and the bottom. So those stay exactly the same. And importantly, when we do this material transformation, we are not going to change the overall height of the beam either. This distance is going to remain h. So it's very important that you do not transform dimensions that are perpendicular to the axis of bending, because those dimensions affect the variable y in your equation for stress, my over I, and you don't want to screw with those variables. What we are going to do is say that if we transform the foam into fiberglass, instead of having this piece of foam that took up the full 4-inch thickness here, or the 4-inch width, we could get away with having a piece of fiberglass that was much thinner, some thickness T prime, and because the fiberglass is stiffer than a foam, a very small piece of fiberglass would deform equivalently under the influence of a bending moment to that foam. Okay. So T prime is really easy to find, because T prime is just the ratio of the two moduli of elasticity multiplied by the original thickness here. So we've got the modulus of the foam multiplied by the modulus, or divided by the modulus of the glass, multiplied by the original thickness, will give us our transformed thickness T prime here. Okay. So putting in some numbers here, we've got 300 KSI, and then we've got 16 times 10 to the 3, and we're multiplying by 4 inches, so we'll get our new thickness T prime from that. Okay, let's see what that comes out to be. 0.075 inches. Okay. There we go. Okay, now when we want to consider stresses in the fiberglass here, what do we want to do? So let's take this right-hand side and flip the equation over so that's our left-hand side. So we want to take 0.1 multiplied by the ultimate strength of the glass. That's the requirement that we have to meet. And then we want to set that equal to the maximum stress due to bending within the fiberglass, okay? So the maximum stress due to bending within the fiberglass is simply going to be given by, let's just write that down again, the maximum stress, right? And what's the maximum stress going to be? Well, it's going to be the maximum value of internal moment, right? The maximum distance y that we can go away from the back axis of bending. And then the trick is that when you're dealing with a composite beam that you've transformed, the value of I down here, which is IXX, needs to be IXX for your transformed beam here. So we'll just call this IXX trans for the transformed beam. Okay. So we have to do a couple of different things to solve the problem here. We've got to figure out what our maximum moment is, and then we've got to figure out what IXX is for our transformed beam. Neither of those are difficult. We're already dealing with the cross section here, so let's just go ahead and figure out what IXX is for the transformed beam while we're at it. I'm reserving this space, of course, for the shear and moment diagrams. So we'll look at doing this. Okay, so we want to find IXX for an I-beam here. Okay. Not difficult to do, because for an I-beam, what we can do is we can do IXX for the whole outside here, and that has a centroid exactly equal to the centroid location for the I-beam, and then subtract off the values of I for the two gap regions, and we can do the super simple position there because all three of those centroids that we're dealing with lie along the same axis. Okay, so here we can go I transformed is going to be I for the outside minus 2 times I for the gap regions. Okay. All right, so let's go ahead and do that. I for the transformed beam is equal to I for the whole outside perimeter, 1/12, the base, which is 4 inches, the height here. The height is going to be h plus 1/4 plus 1/4 inch, so h plus 1/2 inch, h plus 0.5. Okay, and we're cubing that. Okay, and then we're subtracting 2. Well, actually, rather than doing 2 times the gap, we can just do 1 combined gap. That's easier here. So we'll erase that 2 and just consider these 2 hatched areas as being combined into 1 area. Same difference. 1/12. So the base for this combined gap region, so both of these bases added together, is what? 4 inches minus our value of t prime. So we've got 4 minus 0.075. And then we're multiplying this by the height here, which is our value h cubed. Okay, so there's our expression for I for the transformed beam. Okay, and it's got the h's in it that we're looking for. All right, so we've got this side of the equation done. We've got I for the transformed beam figured out. Y max, that's pretty easy to get, right? Because we're just talking about the maximum distance that we can get away from the axis of bending, which is either all the way to the bottom or all the way to the top. So in either case, Y maximum is just 1/2 of h plus 1/4 inch. So we know what that is. So we just need our maximum moment, M max. Okay. So let's go ahead and draw the shear and moment diagrams then for this. Shear diagram and moment diagram. Now this whole thing's symmetric in terms of the free body diagram here, left to right. So our diagrams should be symmetric, left to right as well. And I'm just going to draw the general shapes of them, and then we're going to find the values that we need to find once we've got the shapes drawn. Okay, so this would be in units of pounds, and this would be in pound feet here. Okay, so shear diagram starts at 0 and ends at 0. And here we've got positive values, right, of distributed load. We've got upward distributed loads here. And the magnitude of the distributed load is increasing as we move from left to right. So the slope has to be positive and it needs to be increasing. Okay, so something like that. Maybe I'll go a little bit less on that final slope. There we go. Okay. Then we've got constant values of distributed load. Okay, so we need to have a constant positive value, so constant positive slope. So I'm just going to continue along from the slope where I left off and draw a straight line, right? And then we've got a downward point load, so we're going to jump down. Okay, and then knowing that this whole thing's symmetrical left to right, we just want to mirror this over and draw the exact mirror picture of what we just drew. Okay, there we go. Right, so constant values, constant positive slope, decreasing positive values, decreasing positive slope. There we go. All right, so now let's do the moment diagram. Okay. So what do we have? We don't have any point moments along the ski or along the beam. So all we need to do is look at the shear diagram to draw the moment diagram. Positive values of shear that are increasing. So the moment diagram needs to be increasing positive slope. So something like that. Okay. So increasing positive slope. And then the moments or the shear values flip to negative. So the slope of the moment diagram needs to flip to negative, and the values of shear become increasingly small. Negative values, so the slope has to become an increasingly small negative slope. So matching curve back to 0. Okay. So here's one of those situations that we talked about at the start of tutorial, or that I was talking about at the start of the tutorial, right? In this case here, we want the maximum moment, right? That's the value that we want. We know exactly where the maximum moment is. It's right in the middle of the ski. So rather than going through the process of calculating this area and calculating that area and adding them together, which requires getting an equation for this line and then integrating it and then calculating the area of a rectangle and a triangle and adding those together, we can just do a section cut right at the location of our maximum moment and analyze 1/2 or the other half of the free body diagram to figure out what M max is. Okay, so let's go ahead and take that section cut and do that. Okay, so taking our section cut. There we go. Just check in case anybody has the question. Let's see. Okay, somebody commenting that they wrote a bunch of stuff under the free body diagram, and now there's no space. I should have given you an advanced warning of that. That was mean of me. Sorry. I'll take the blame. Okay, so here we go. I don't need to answer that call right now. Let's see. We've got this portion of the distributed load acting upwards like that. Great. This value was our value W right there. Now, the question is, do we include the 180-pound load or don't we include it? Well, right, decide whether or not this point of maximum moment is just fractionally to one side of the 180-pound load or the other side. I'm going to say we're going to include the 180-pound load. The answer about whether you include it or not is that it doesn't make a difference what your choice is, whether you include it or not. It's going to affect the internal shear present, but it's not going to affect the internal moment. So in terms of internal forces here, we've just done a section cut. So, right, we know we can have an internal shear force V, an internal normal force N, and an internal moment M. Okay, there we go. And this is M acting about the centroid of this cross section, which we'll call point A. So here's M about A, and this would be V subscript A and N subscript A. Okay. All right. We're not interested in N in this case. Well, not only are we not interested in N, but N is 0 if you do sum of the forces in the X direction. What we're not interested in is in V in this case, because we're only interested in the internal moment M. Okay. So let's figure out what the internal moment MA is, and that is, of course, the value of our maximum moment M max. So doing a sum of the moments about point A, which has to be equal to 0, would give us the value of M max. So you see, around in one direction we have M max, around the other direction we have the moment from the resultant force on the snow. So we've got M max has to be equal to the moment caused by this force here. So what do we have? We've got a value of W multiplied by, let's break this up into two pieces and do the moment created by this, this rectangular piece first. So that's going to be W multiplied by length, which is 1.5 feet here. And then multiplied by the moment arm. So it's going to be 1.5 divided by 2. And then plus the moment created by the load in this piece of the resultant load here. So that's going to be, for a resultant, 1/2 of the base, which was 1.5 feet, multiplied by the height, which is W, multiplied by the moment arm, which is, this is 1.5, this is 1.5. Right, so it's going to be 1.5 plus 1/3 of 1.5. 5 plus 1/3 of 1.5. Okay. And I'll leave that on the board for now. All right, so we could figure this out if we knew what W was. Do we know what W is? No, we don't know what W is. We could know what W is, though, because we could just do some of the forces in the Y direction for this whole free body diagram and get a value for W. right? So let's do that. Okay, I just erased that equation, which we'll need to put in later, but I've got it written down elsewhere. Okay, so for this whole free body diagram, we'll do sum of the forces in the y direction is equal to 0, and that is 180 pounds is equal to the total upward force, which is W multiplied by 3 for the middle portion, and then plus 2, right, of the little triangular pieces on each end. So those have a resultant of 1/2 the base, 1.5, multiplied by the height, which is W. Okay, and that's going to give us W in units of pound-feet, because we're working in pound-feet there. What did I get when I solved for W? 40 pounds per foot. There we go. Okay, so now we can go ahead and put W back in down here and solve. So now with W is equal to 40, should be comma, M max. Okay, put your 40s in for W, evaluate that expression there, and you get the maximum internal moment is 105 pound-feet. 105 pound, try that again, pound-feet. Perfect. Okay, everybody with me so far? So now we've got, look at this, we've got all the components of our equation here with tick marks, so we can get on to evaluating it now. Give ourselves some space to do that neatly here. All right, so our equation that we're dealing with for solving the problem is 0.1 multiplied by the ultimate strength of the glass is going to be our maximum moment, maximum value of y, all divided by I for our transformed beam. Okay, great. Let's start putting in some values. So what did I say was the ultimate strength of the glass? I think I said 20 psi. Yep. 20 times 10 to the 3. Remember to change that to psi. And then our maximum moment is 105. But we want everything in units of pound inches psi. Feet here, so we want to change that into a moment that's in pound inches. That means multiplying this number by 12 there. Then our maximum value of y, again here in our transformed beam, we are having a maximum moment that's occurring about a horizontal centroidal axis. So the farthest we can go is all the way to the top or all the way to the bottom of the cross section, which in either case is our unknown height of the foam divided by 2 plus an extra 1/4 inch. So you've got h over 2 plus 0.25, all divided by I for the transformed beam, which would have been 1/12 base height cubed minus 1/12 base of the gap region would be 4 minus 0.075 height cubed. Okay, there we go. All right, great. So solve for h, and you get the required height of the foam in the middle of the sandwich for that ski, right? That would be required so that under the loading situation shown, we'd only be at 10% of the fracture stress for the fiberglass. So there's H. So H equals, when I put this into my calculator and asked it to solve the equation for me, it gave me 0.549. 0.549 inches, and we were asked for that rounded to the nearest 16th of an inch, because presumably they only sell these foam inserts in increments of 16th of an inch. So again, the easiest way to do that is just to take 0.549 and see how many times 1/16th of an inch would fit in there. And did I do that calculation? I did do it, but I just don't have the decimal value shown for what that is. I only have the final rounded answer. So let's see, 0.549 multiplied by 16 is 8.78. Okay, so there can be 8.78 1/16 into 0.549. That means that we have to round upwards, right? Therefore, H is 9/16 of an inch. Okay. Because if we went down to 8/16 of an inch, we would be above 10% of the fracture stress. Okay, I'll give you a minute to copy down the final piece and digest and think about whether you have any questions about that problem. Yeah, absolutely. I can say the wording of the problem itself again. Okay, so I'll read it word for word here without. I know it's difficult when I'm always pausing to write down critical pieces of information. So, the problem statement read like this: a 180-pound man stands on a single ski. The ski has a foam core with a modulus of 300 ksi. Sandwiched between two 1/4 inch thick fiberglass sheets of modulus 16 times 10 to the 3 ksi and ultimate strength 20 ksi. If the maximum bending stress for the given loading situation should be 10% of the fracture stress of the fiberglass, determine the required thickness of the foam to the nearest 1/16 of an inch. And you know what? Because that's kind of a wordy problem compared to the ones we've been doing, I'll pop a copy of that up on Brightspace for you too. It'll just be labeled Tutorial 6. All right. Now, if the other thing to understand about composite beams is to find a stress within the fiberglass, right? We just use this normal equation for bending, right? Here we were finding a stress within the fiberglass, and the fiberglass was the material that we didn't transform. Okay, so we took this and we transformed it to something that was all fiberglass, but the fiberglass on the top and the bottom, where we were actually calculating the stress, that was material that hadn't been transformed. If we wanted to calculate a stress value within the foam, which is the material that we did transform, then we do this in exactly the same way, except that we need to multiply this equation for stress by the ratio of the moduli of elasticity. So if we wanted a stress anywhere in the foam, right, we'd do the same thing and do my over I, and using I for the transformed beam. But because we're using I for the transformed beam, and actually the material that we're calculating the stress in is a different material, we have to multiply by the ratio of the moduli of elasticity here to get the actual stress in the foam. So that's the only other thing to keep in mind. But usually when you're doing these problems with composite beams, you're generally not interested in the stress within the actual filler material. You're more interested in the stress in the strong and stiff component of the composite beam. The filler here is only present to increase the total height of the cross section and not to provide strength, right? And increasing the height of the cross section is highly effective because for moments about the horizontal centroidal axis, stress is proportional to 1 over h cubed. So if you increase h by a small amount, you decrease stress by a large amount, right? So the power of composites is increasing h without adding additional, much additional weight. Okay, those are all the problems that I wanted to do with you today. We'll have a longer tutorial or back to normal sort of length tutorial next week when we do some problems involving transverse shear stress in beams. Okay. So again, like usual, I'll just stick around as people leave and I clean off the whiteboard to answer any additional questions anybody has. For the rest of you who are heading out, I will be here same time, same place next week, and we'll see each other then.